Now, we have dealt with the Fourier transform, Fourier integral theorem. Well, let me just enunciate the theorem to start. Fourier integral theorem. I introduced what is called the Fourier transform. The Fourier transform is f of k, and it's calculated from 1 over 2 pi integral minus infinity plus infinity f of x e to the minus I kx dx. And that allows us to compute a function f of x in the shape of an integral, like the integral of f of x e to the I k of x. Well, this is f of k. F of k e to the I kx dk minus infinity to plus infinity. Okay, so that's the Fourier integral theorem. You can write any function in the shape of an integral of this type. You need to calculate this coefficient f of k. And the method to calculate f of k is to use this formula here. You simply take the function that is provided, multiply by e to the minus I kx, and do the integration to get the f of k. Notice that the integration here is dx. Element is dx. Here is dk. When you integrate, you want to get f of x finally, there must be no k in the problem. So whatever k appears here, you replace it with these limits. So only x will survive, as you require. Now, this 1 over 2 pi appears here, it doesn't appear here. By the way, there was an error I had in the last problem, last lecture. I corrected it on the website, okay? So you'll see that there is a correction. There's just an I missing throughout, but at the end of the game, the I was important because we needed the complex value. But I wrote the correction, it was just one line. Yeah, now I'm making the point that it's 1 over 2 pi, it looks like a lack of symmetry here. There are various versions of the Fourier integral theorem. You could have 1 over root 2 pi here. And here you can have 1 over root 2 pi. Then it's symmetrical. Or you can have the 2 pi there and nothing here. And 1 here. There's many ways of writing it, but this is a form I recommend we will stick to for our calculations. Sometimes in resolving this integral, here, or this here, we transform, the function f of x may be something over something, n of x over d of x, in which case there will be things like poles. In those cases, you have to invoke the residue theorem. Unless it's a very transparent thing like 1 over x squared plus 1, which is arctan, then the game is over. But then, if it's tricky things like 1 over x cubed plus x, 1 over x to the 6 plus 1, then you need to use residues to calculate that. Otherwise, there's no other way in many cases. There's also e to the minus I kx, it goes with it. So, clever integration by parts and stuff won't work in the most cases. But you don't always have to use residue theorems. You can use ordinary calculus wherever it can be used. If there's no poles, then there's no need for any heavy lifting. You don't have to use residue theorem and stuff. You can just do the integration like normal. But I did show you something called the principal value of the integral 2 lectures ago, where if you want to consider just the imaginary part of an integral, or just the real part, you can switch real and integral under certain circumstances, provided the functions are absolutely convergent. And in most cases, the functions will be of that type that you come across here. So let's take an example. I want to deal with this example in the textbook, example number 85, because it has got some nice ideas in it. Example 85. You may notice it appeared in the exam a few times. Find the Fourier transform of f of x equals to e to the minus absolute x cos x. So that's the f of x there. You need to calculate the Fourier transform for that function. So in trying to find that Fourier transform, so in other words, you've got to find this left-hand side guy. Yes. 1 over 2 pi e to the minus absolute x cos x e to the minus ikx. So that's the integration we have to do. Looks quite dangerous, but let's see how it can be done. So first, observe, note, f is even. This may help us to double certain integrals if necessary. Or an even times an odd becomes an odd, in which case integral from minus a to plus a becomes 0. Things of that type will be of relevance when we do this calculation here. So let's turn it out. F of k is 1 over 2 pi integral from minus infinity to plus infinity e to the minus absolute x cos x e to the minus ikx dx. Now you can write this e to the minus absolute x. This part here, e to the minus ikx. Okay, let me write it in full. Cos x times, this is actually cos kx minus I sine kx. You agree with that? That's Euler's theorem. E to the I theta is cos theta plus I sine theta. If there's a minus there, there'll be a minus I in the middle. But the relevance of that is that cosine is even, but sine is odd. This guy is even, this guy is odd. And we know this guy is even for sure. These two together. So you got even times even. That will be okay. That can happen, right? That will not become 0. But then if you do even times the odd, what happens there? That dies off. See, so this even section here times the sine kx, and you integrate it from minus a to plus a, the same two limits here, one negative, one positive, that will give you a 0. So then this thing can be written in the following way. 1 over 2 pi integral minus infinity to plus infinity e to the minus absolute x cos kx dx. And okay, at this stage, let me just leave it as it is instead of changing. Okay, what I can do is, you see the cos x cos kx, 1 over 2 pi integral minus infinity to plus infinity e to the minus absolute x. I'm trying to save a few lines here. But this can be written as cos k plus 1x plus cos k minus 1x dx. All upon 2 times half. You know that formula for cos of A plus cos of B that we came across in the first part of the work. This thing can cancel with this. Oh, actually, that doesn't cancel with the half. But what happens here now? I can double this. I can double this and get 1 over 2 pi integral from 0 to infinity e to the minus x into cos k plus 1x plus cos k minus 1x dx. I double it. So this 1 over 2 here and the 1 over 2 is 1/4. Double that, it comes back to 1/2. Notice that. It looks a little sinister, but that's how it happens. It's 1 over 2 times 1 over 2 here, 1/4, and then I doubled by taking half the length there. Now from here, the game is played slightly differently. We can now invoke this idea of principal value, and the cosine k plus 1, we should realize is a real part of certain exponential function. So this is 1 over 2 pi integral 0 to infinity e to the minus x. The cosine k plus 1 is the real part of e to the k plus 1, I k plus 1 x. And the cosine k minus 1x is the real part of e to the I k minus 1x. So remember, e to the I theta is cos theta plus I sine theta. That's Euler's theorem. The real part of e to the I theta is just cos theta. I'm saying backwards, cos of k plus 1x is the real part of e to the I k plus 1x. I'm using the same result there, the real part. And now I can put this real part outside using the principal value idea, which we dealt with in the previous lecture. So this becomes 1 over 2 pi, real part of integral naught to infinity, e to the minus x plus I k plus 1 x plus e to the minus x plus I k minus 1x. I'm just applying the exponent laws, the laws of exponents. Add the exponents there, add the exponents there. And put real outside. It makes the integration a lot easier. So this becomes 1 over 2 pi real part of. So integrate this, it will be e to the minus x plus I k plus 1x over minus 1 plus I k plus 1 plus e to the minus x plus I k minus 1x over minus 1 plus I k minus 1. And the limits are naught to infinity. Now, here comes a neat idea which is not obvious, but when you substitute infinity here, this becomes 0. Why? When you substitute infinity here, this becomes 0. Why? Well, look at this here. Look at the green e to the minus x. If you plug in infinity, e to the minus infinity, it's like 1 over e to the infinity. It's like dividing 1 by a huge number. Isn't that 0? That will be 0, and whatever happens here, even if it's real, unreal, doesn't matter, 0 times that will be 0. There's an I here anyways. It's a complex number. But the fact is, e to the minus infinity will produce a 0. It will kill the entire thing here. So when I substitute infinity, that's 1 over 2 pi, real part of. So I will get 0. 0 plus 0. Then I must subtract by substituting 0. Now, when I put in a 0 here, e to the 0 and a 0 here is 1. And you'll end up getting 1 over minus 1 plus I k plus 1 plus 1 over minus 1 plus I k minus 1. Right, so now we just churn out the result, 1 over 2 pi, real part of. Put the minus in the brackets, it will become 1 over 1 minus I k plus 1. Subtract, oh, you can put a plus here, 1 over 1 minus I k minus 1. Yeah, I just multiplied this negative by the denominator. So I can leave this as a plus. Can't do it to both. Do it to 1. Minus times minus is plus, and you get a minus here. I'm still aiming to find the real part of this. So far, the i's are in the denominator, so that doesn't help me. But I can now do some switching around. Multiply by the conjugate, 1 plus I into k plus 1. Over at the bottom, if you multiply by the conjugate, it will become 1 squared plus k plus 1 squared. Plus. Here you multiply by the conjugate, 1 plus I into k minus 1. At the bottom, it will be 1 plus k minus 1 squared. In conclusion, we now read off the real parts. The real part is this, the ones. If this problem had a sine x in it, you would need the complex part. Then you read the k plus 1, k minus 1 part. This problem has the real part, it's a cosine problem. So the answer now is 1 over 2 pi. The real part of that is 1 over 1 plus k plus 1 squared plus 1 over 1 plus k minus 1 squared. That's it. That's f of k. So what that means is that f of x, the function f of x, is simply the integral from minus infinity to plus infinity, 1 over 2 pi, 1 over 1 plus k plus 1 squared, plus 1 over 1 plus k minus 1 squared, e to the I kx dk. Your textbook has got a number of mistakes there where the dx and the dk are not correct. I'll do them correctly here on the board, but just be aware of the fact we have quite a few mistakes. When it's a small f of x, the integration will be for dk. That's how we write a function in the shape of an integral. But really, what we will be aiming for in this section of the work, guys, is that we simply to find the Fourier transform. Oh, there's a part missing here. That's not aligned. You should have told me, I would have avoided writing it. F of k in the vector. You see, this f of k is known as the Fourier transform. This is going to do a job. It's like a tool in mathematics. Remember the Laplace transform from last year? Integral e to the minus ks from minus infinity to plus infinity. The Laplace transform had certain properties that you could use to solve differential equations. This has similar properties. It'll be used to solve the heat equation and the Laplace equation squared as we go along. Any questions about that derivation then? Any parts that you're finding a little suspicious? The only trick there was the interchanging of the real and the integral, but then we justified that in the previous lecture on principal value. You'll have to read that section there if you were not present for the lecture. Now, we go on to the Fourier sine and cosine integral. Fourier sine and cosine transforms. Like we had Fourier sine series, Fourier cos series. Those were the original ones. Then we had the exponential one at the end. In this formulation here, we start off with the exponential and then we break up into sine and cosine. Cosine is the even part, sine is the odd part. That's the simple idea we keep on applying. Now, let's say a function f is even. Say f is even. I'm going to give you the short route here. There's a long route as well, but time doesn't permit. Then f of k will be 1 over 2 pi integral f of x e to the minus I kx dx that we know already. Minus infinity to plus infinity. But if f of x is even, remember this is cos kx minus I sine kx, as we've done in the previous example. If f is even, then even time even still survives. And I can double and say this is 2 over pi. Okay, let me just write this as, I'm confused which notation to use. Should have sorted the notation out. 1 over pi, it's actually 2 over pi. Integral from 0 to infinity, f of x cos kx dx. And if f is odd, likewise I'll get f of k, which is normally 1 over 2 pi integral minus infinity to plus infinity, f of x e to the minus I kx dx. This time Odd times odd will give you even, so the sine part will survive. So it will become 2 over pi integral 0 to infinity f of x sine kx dx. So those are known as the Fourier sine and cosine transforms. Not quite yet, not quite. I'm just explaining what happens if you have odd and even. I will define it. But we can make a note. This is an observation we can make at this stage here. Note, if f is odd or even, then capital F is also odd and even in the same order. When you perform the integration of an odd function, in this case here, it will become odd and likewise even. As I said, the Fourier integral is a tool. So these constants, 1 over 2 pi and stuff, I can play with them and put them in a convenient spot where I want. So far, I haven't done anything illegal. I will soon do something illegal. Also, by symmetry, we can say that, okay, say f is even again. Then f of x will be an integral from minus infinity to plus infinity, f of k, e to the I kx. The behavior is exactly the same, dk. I want to arrive at a definition that's suitable to us. Minus infinity to plus infinity, f of k cos kx plus I sine kx, same thing, dk. Again, odd and even story. So we can double integral from 0 to infinity, f of k cos kx dk. dk. You see that 2 there, and the 1 over 2 pi on the top. So we make the following definitions. So from here onwards, you can use these definitions, which are motivated by these symmetry properties. Fourier cosine transform is f of k, and we put a small c there to say Fourier cosine transform. We will define it as 2 over pi integral 0 to infinity f of x cos kx dx, and this will imply that f of x is just, will have nothing in front. We'll absorb the 2, 0 to infinity f of k, that's a cosine, cos kx dk. So that's a Fourier cosine transform. We define it in such a way that 2 over pi appears here. So for f of x, there's nothing in front. It is analogous to the Fourier series, in back. For the sine and cosine, you have 2 over L. So that's the same kind of behavior that we have here, except that the sigma now is an integral. And for completeness, let me just write down the Fourier sine transform. Fourier sine transform exactly the same appearance. We can say fs of k will be 2 over pi integral 0 to infinity f of x sine kx dx. that implies and is implied by f of x, never both sides, is integral from 0 to infinity f of k cosine, sine kx dk. Moral of the tale is it goes from 0 to infinity, and it's 2 over pi there, and there's 1 there. These are the definitions. You'll find that this part is not important. This Fourier transform is important. I'll need this guy to convert certain equations into certain algebraic forms. So functions can be either even or they could be neither. If they're neither, then you could either have a sine or a cosine transform. You remember when we dealt with the series, I told you that if you want this cosine transform, we create an even extension, something on the left, which appears for free. It doesn't have any importance, it's just something that appears. If you want the Fourier sine transform, you will get something in the third quadrant, which is like an odd piece. It's the odd extension. A similar concept happens here. Okay? So any function can be written with a Fourier sine or cosine transform. They don't have to be even or odd. So those are definitions, and now can be applied in general. So, for example, 86 is a nice example that unifies everything. Find the Fourier cosine and the Fourier sine transform of f of x if f of x is 1 minus x squared for absolute x less than or equal to 1 or 0 elsewhere. Now, this would be an interesting example because I'm not really interested in the final answers for the Fourier transform. So what I will be interested in is the pictures. What the graph looks like at the end. What does the Fourier function, what does the function represent in terms of the Fourier transform? That's what I'm going to be aiming at largely, but let's write down the solution to the problem. So the first one is the Fourier transform, f. So we know f of k is 1 over 2 pi integral from minus infinity to plus infinity, 1 minus x squared. Well, let's write f of x first because the limits are different. So f of x e to the minus I kx dx, it becomes 1 over 2 pi. Okay, you should observe that this is an even function also. That helps. So 1 over 2 pi times 2 times integral from 0 to 1. You see, this absolute x less than 1 means minus 1 less than x less than 1, right? But because it's an even function, I can double it and go from 0 to 1 to make the calculation easier. 1 minus x squared cos kx, because it's the even part that will survive, dx. And when you calculate this, I'm not going to do the whole details, you'll get 2 into, don't worry about the answer, sine k minus k cos k. I hope you don't come back and tell me in the exam when I mark your stuff wrong that you said don't worry about the answer. No, actually, I mean for this particular problem, it's going to be tedious to calculate this. You have to give this integration by parts a few times. You see the x squared cos kx, integration by parts twice. The limits are no longer infinite. It's 0 to 1. It was infinite, but then this thing is only alive between minus 1 and 1. And using the symmetry, we go from 0 to 1 by doubling it. So you'll get that answer at the end. Twice integrating by parts. And then you can write f of x will be 2 over pi integral 0 to infinity sine k minus k cos k over k cubed e to the I kx dk. That will be the function. And this will become 1 minus x squared if absolute x is less than or equal to 1. It will become 0 elsewhere. And as a plot, 1 minus x squared, what is that? Like this. One minus x squared and 0 elsewhere. Okay, so that's the shape. Notice it's even, so on both sides it looks the same of the y-axis. Y-axis is an axis of symmetry. I think you can guess that the cosine function will look the same as well. It happened to have cosine here. The sine part disappears. But there will be a minor difference. So B. Let's take the Fourier cosine part. Fourier cosine is defined to be 2 over pi, integral naught to infinity, f of x cos kx dx. That's 2 over pi, integral naught to 1 minus x squared. What is the answer here? 4 sine, yeah. Cos kx dx. Answer here is same kind of thing, but with a 4 in it. 4 sine k minus k cos k over pi k cubed. Which implies that the function f of x is integral, well, 4 over pi here in front, integral from naught to infinity, sine k minus k cos k over k cubed e to the I kx dk. And that gives you 1 minus x squared. If absolute x less than or equal to 1, it's 0 elsewhere. So that is quite a harmless problem. It's the same as the previous one. The fact that there's a doubled value, it means nothing actually. In fact, this is like having the right-hand side only, and this is like the even extension that was formed there for free, which is not actually required. But there will be a difference now with the odd bit. When I take the odd stuff, then this is now dealing with the sine function. Odd terms, you see, you'll be dealing with the sine function, but then, remember, it will be 0 to 1. It won't be minus 1 to 1. That's the problem. It's from 0 to infinity, so it's only the positive side, 0 to 1. So you can't say that's 0. Integral of odd is 0 because it's not minus a to plus a. You have to actually turn it off by hand. But the graph there is going to be interesting. So we then come to the C case Fourier sine. The Fourier sine transform will be 2 over pi, see, this is the definition, naught to infinity, f of x sine kx dx. That's 2 over pi integral naught to infinity 1 minus x squared. This is naught to infinity sine kx dx. Crank this out. Answer is not 0 because it's not like even times odd. Being odd, the limits are not minus a to plus a. So you have to really crank this out by hand. And when you do that, you will get an answer that looks like this: 2 over pi, just write this down, 1 over k plus 2 sine k over k squared. It doesn't look anything like the previous one. Minus 2 into 1 minus cos k over k cubed. Turns out to be that. It's some function of k. There's no x anymore. That's a transform. It will do some job later on. And once we have the transform, we can write the function f of x as 2 over pi integral naught to infinity 1 over k. A bit tedious writing this a few times, but I'm not going to do it often. Plus k over k cubed dk this time. dk. Now you see there's going to be a bit of a problem here. So let's see what we actually want. So we are dealing with this guy here, 1 minus x squared. I said when you do the Fourier cosine bit, you get an even extension on this side to finish it up. Now you're going to get an odd extension because the sine function. Where will that be? What's the odd version of this guy? How would you draw that? Where's the odd piece? So don't you think it'll be at the bottom here? Minus 1. Like that. So this is what we want. And this is what we get with it for free. Okay, so that's because of the fact that we chose a sine, Fourier sine transform. In other words, this thing evaluates to 0 if, okay, x, not absolute x. If x is more than 1, it evaluates to 1 minus x squared between 0 and 1. What does it evaluate to at exactly 0? When the x value is 0, what's the y value? You have plus 1 there and minus 1 here. What have we learned about at the jump discontinuity? Where does it finally settle down? At the average, at 0. So then the last part there, oh, what about this reverse part here from minus 1? So from minus 1 less than x. Oh, goodness. Things are happening on my machine here. Minus 1 less than x less than 0. It's this part here, the reverse parabola. So this is x squared minus 1. X squared minus 1. And lastly, it comes back to 0 provided x is less than minus 1. So there are 5 pieces, you could say, in this curve. This function here is actually this thing here. You plot it. This is the odd extension for that shape there. Any questions? So we haven't done the donkey work, dirty work. The dirty work is that we do. compute the integral and get these answers. And then we will go and try it out. I will always have the students try this out by themselves. Don't forget, next week we have a test, eh? And it's a type test. It's on a Tuesday, and on the Wednesday I have to release the DP refusal list. So we're going to be marking overnight. It's going to get tricky. Yes? Not really, not really. So here, one belongs to both. You can put the equal sign on one of them, but it's not a crucial thing. Any other questions? If you're very religious, you can put them in one place, at least in one place, so it's covered. So then now everything is covered. Okay, just one last problem then before we stop with the work for today. Then I'll give you some time to ask some tutorial problems. We didn't have tutorial time on Monday because of the I gave a lecture. So in case you have been working through the problems, which I expect you have been doing by yourself, then you can have a chance to ask some advice on that. Now, find the Fourier sine transform of f of x equal to e to the minus cx. C is a positive constant. C is just some number. It's a harmless problem. But again, I'm interested in the graph at the end of the game. What does the final thing look like? Well, we're asking you to find the Fourier sine transform. So you should have an order extension. So let's just crank it out with the formula. Solution. Formula Fourier sine transform is 2 over pi integral f of x, e to the minus cx, sine kx dx from 0 to infinity. So the sine kx, we realize, is the imaginary part of e to the I kx dx. Sine kx is the imaginary part of e to the I kx. So e to the I kx is cos kx plus I sine kx. The imaginary part is sine. So that imaginary part there, it makes the integration easy, as you can see. I don't have to use integration by parts, although you can do this with integration by parts. This is quite easy. It's down your street. It's one of the ones I do in first year. And there's a, what is the trick that happens at the end of this game? Remember this problem in first year? It's one of those innocuous ones that at the end you have to do something. You have to move something from this side to that side. If you get an e to the x sine kx appearing here at the end of minus that, you take it across and you get 2 of them. And you divide by half. That was a tricky one from first year. But now we can use some more sophisticated tools like the principal value theorem. This is 2 over pi, imaginary part of, integrate this, it will be e to the minus cx plus I kx over minus c plus I k from 0 to infinity. And then once again, as I argued before, e to the minus cx, if you're going to infinity, e to the minus infinity is like 0, 1 over 0. 1 over infinity, I mean, is 0. Irrespective of the other thing here. But again, if you're ultra religious, as happens to some of us, and it's good to be that way, you may recall that, well, actually, no, there's nothing to be scared about. You see, this part here, if it's 0 times infinity, if you got 0 times infinity, then that's not straightforward. If you remember from first year, That required things like L'Hopital's theorem and making it into a Lin and stuff. That's not trivial, but this doesn't happen here. This is some positive thing, e to the ikx. So you can use L'Hopital's theorem and argue that, but I can tell you the answer is going to be 1 there, or 0, so we won't go into the details. Then we will, so it'll be 0 minus, now plug in a 0 for x, it will be 1 over minus c plus ik. Okay, that's 2 over pi, imaginary part of 1 over c minus ik. Obviously, it's good to multiply this by c plus ik over c plus ik, where we can actually find the imaginary part. So it will be the imaginary part of c plus ik. At the bottom, you'll have c squared plus k squared. And the imaginary part is just k. So the final result will be 2k over c squared plus k squared. Okay, so the imaginary part is k. This is the real part. If you were dealing with the Fourier cosine series, then you would read this part, c. It will be 2c. So finally, you can write f of x as 2 over pi no, actually, there's no. Oh, where's the pi here? Yeah, sorry, I missed out the pi here. Yeah, 2 over pi, integral from 0 to infinity of k over c squared plus k squared sine kx dk. Now the question is, what does this look like? Remember, f is e to the minus cx. And c is positive, so it's like e to the minus x. E to the minus x, and e to the minus 2x, and minus 3x. What kind of a graph is that? E to the minus x. Exponential function. Normally, exponential function goes like that. So this is negative in the exponent, so it goes backwards. So it'll be something like this. Crossing through 1 there. Let me just make that a little clearer. Too tight. I'm using dotted lines because we don't want the entire thing. We want only the part that's from 0 to infinity. This part here. That's a function e to the minus x. It goes through 1. Goes through 1 there. Now, where's the other part? Where's the partner for this? We chose sine kx, so there'll be a free odd extension. Where's that? How would you draw that? So 1, you have minus 1. So you have to draw it something like that. That will be the odd extension which you get for free. Odd extension will be here, minus 1. Right, so that's the shape. Minus 1. So you can say that this gives you the function e to the minus cx if x is more than, oh, I made a mistake here. Yeah, this is like more than 0, e to the minus cx. What does it give you if x is 0? What do you get if x is actually equal to 0? Yeah, the jump discontinuity. It's 0, right? It's the average of minus 1 and 1. So that will be 0. And how do you describe this other one here? What's the equation of this? If you take a reflection of this guy in the y-axis, so the x will become minus x. This will become e to the cx. E to the cx. And if you take a reflection of this guy, isn't it this guy? Isn't it negative e to the cx? Negative e to the cx if x is less than 0. That's the three pieces of graph that we need there for this problem. Okay, so that's the Fourier sine transform, Fourier cosine transform, and the Fourier transform. The formula is the 1 over 2 pi minus the sine and cosine, the two of them are going to end up a non, so 2 over pi, but a non-two. And then we just crank out the integrals. You notice I didn't use the remainder of the residue theorem anyway. That's just the trick also. It's a tool we need for certain types of integrals. We're not going to use it all the time. When necessary, if you've got a numerator divided by a denominator, they have poles involved. You don't have that here. Function was what? E to the minus cx. There's no poles. It's going to homomorphic everywhere. And missing everywhere. Alright, so in the next lecture, I will deal with the heat equation and the Laplace equation. That will be on the Monday. And then the Tuesday, we'll bring it to an end. Then the Thursday, we should have some time for more tutorial. On Monday, we probably have one period of lecture and one period of tutorial, because you may want questions, ask some questions before the test. Nobody asks questions. That's the funny thing about this class. You guys are a bit of an unknown quantity. Oh, by the way, I made an appeal to you to please pull in the student evaluations, right? Many of you don't attend the lectures, many of your colleagues, and then it looks very bad in the student evaluations and the response rate is only 20%. It means that the lecturer was not doing his work properly or something like that because students didn't care, which I don't think is a fair reflection. You should actually write what you think, but you need to be fair. All right, I'll stop here. If you want to continue sitting around asking some questions, that's fine. I'll stick around for a few minutes. I won't be here too long because I've got to catch a flight to Pretoria, to Dover. About finish, but I still have a few minutes.